Okay, y'all, last video for chapter 15, so yay. Also, this one is super short, which is also yay. So this one is about Le Chatelier, which is what your lab will be over on Wednesday. So for Le Chatelier, we're going to use that to predict the effects of changes in conditions on where the equilibrium lies. Okay, so we've got our equilibrium, it's established, but then I kind of shake up their reaction a little bit, whether I add something or move something, change the pressure, things like that, even heat it, and then the reaction is going to have to do something else to reestablish that equilibrium. So, some things that are important before we do anything. Doing anything to a solid or liquid does not matter. Okay. Solid and liquids don't count in our equilibrium expressions, therefore they do not affect Le Chatelier's principle. Okay. When I add a reactant, I shift right. Okay, I do want you to know down here, this is super important. Equilibrium constant stays the same because I did not change temperature. The only thing that can change the value of K is temperature, because K is the equilibrium constant. Okay, when I remove a reactant, again, not a solid or a liquid, I'm going to shift towards the piece that I removed. Okay, again, K stays the same. This is super important. Equilibrium will shift away from the side with added chemicals or towards the side with removed chemicals. This also works on the product side. Okay, again, no solid or liquids are affecting it and no effect on K. So this is just what it looks like when I have to reestablish that equilibrium. So I was in equilibrium, I disturbed it somehow, and then it has to go through a process of reestablishing that equilibrium. And remember, equilibrium is where the rates are the same, so where this graph has flat slopes for both the products and the reactants. All right, so let's see. Adding CO2. So remember, when I add, it shifts away. So it will shift left. Adding calcium carbonate. Notice this is a solid, so this has no effect. Okay, let's look at the next one. Adding Br2, we're going to shift left. Adding BrNO, again, it's a gas, so we're going to shift right. So whichever way we add, it shifts away from that side. Okay, for gases, it's talking about the pressure. I'm not concerned about the pressure right now. There's a whole slide on pressures and volumes. But just know that adding means we shift away. So they added a reactant, it shifts to the product side. Okay, inert gases, this is also very important. Adding an inert gas does nothing to it. This is something I did in my research for grad school. And I know some of you listened and you heard that I have 2 physics degrees. I actually did all my research in chemistry, and I wrote my paper on chemistry. I didn't write a thesis because I had 36 hours total, so I didn't have to do a thesis. But my research was chemistry, but it was really that section where they cross, because physics and chemistry do cross. Y'all just don't see it until much later on. Sometimes chemists never see it, but we would use an inert gas, and it would just kind of be a catalyst because it wasn't affecting our equilibrium. Okay. Volume and pressure, I think, are the worst ones. Maybe you'll think it's super easy. But remember, Boyle's law is P1V1 is equal to P2V2. This looks a lot like our our dilution equation, and it is a lot like it. But I do want you to know if pressure goes up, volume goes down. So they're an inverse relationship. Okay, so sometimes it's going to talk about volume and sometimes it's going to talk about pressure, but really it's doing the same thing. So here we say we decrease volume, which means we increase pressure because they're inverse. So the equilibrium shifts to remove that pressure. And the way it shifts is the side with the fewer gas particles. So I would say volume goes down, pressure goes up, fewer particles. And again, we're only talking about gas particles because we don't talk about pressure of solids or liquids. Also, remember, solids and liquids do not affect our equilibrium values. Okay. Again, it talks about K down here. This does not affect K, only temperature affects K. Also, this doesn't affect concentration. We're only talking about pressure. Okay, so here they're talking about Boyle's law, which is what I already told you. And here we can see we increase the pressure, so the piston comes down. Notice at that point, you count your moles of gas on each side. So I've got 4 moles and 2 moles. It will shift to the side of less particles. In opposite correlation, if you decrease that pressure, it's going to shift to the side of more particles. Okay, because their relationship, they're always going to be opposite. Okay, here, decreasing volume. So V goes down, pressure goes up. I count my particles. This side has no gas particles. This side has 3. Okay, so it shifts left to the side of fewer particles. Oppositely, when volume increases, it's going to shift to the side of more particles. And inert gas does nothing, no effect. Okay, there will be some quiz questions on Le Chatelier. We're going to do a lab on Le Chatelier. There's going to be homework questions on Le Chatelier. Le Chatelier is really an important concept. Okay, looking down here, decrease volume. First thing you do, count your moles, 3 and 2. So volume goes down, pressure goes up, side of fewer particles, shifts right. Oppositely, when the volume goes up and pressure goes down, we shift to the side of more particles. Okay, so this one doesn't have a set way because you have to establish how many moles of each particle are on each side, but only the gaseous ones. Okay, now we're going to how heat affects it. So remember, exothermic means we're releasing energy, and heat is a product. And see, you can see it over here as a product. Also, this means delta H, if they tell you, will be a negative value. If it's not in the reaction itself and it says delta H equals, exothermic is negative. And then once it's in the reaction, it kind of acts like concentration. So we're looking at it being a product. If I add heat, it shifts back to the reactant side because it's going to shift away from the way it's added. Okay. This does affect K. Okay, when I shift this way, that means I'm going to the reactants. And remember, when K is less than 1, it shifts to the reactants. And when K is greater than 1, it shifts towards the products. So once it shifts back towards the reactants, that means K goes down. Okay, endothermic is the opposite. It absorbs energy. Heat acts like a reactant, and delta H, if they give it to you separately, will be a positive value. So if I add heat to this endothermic reaction, we're going to shift towards the product side. And a shift towards the product side means an increase in K. Okay, if I decrease temperature, it acts just like I removed a concentration of a reactant or a product, just depending on what side it is. So it's treated just like concentration, except it does affect K. Okay, so here we're looking. It tells us endothermic, which means I'm going to write heat in the reaction. Okay, increasing temperature shifts towards products. Decreasing temperature shifts towards reactants. So this way, this way. Okay, K increases, K decreases. It's a good point to make sure you know what K is doing, but only on what heat is playing into it. That's the only time K is changing. Okay, here we've got another one. Exothermic. So heat is a product. If I increase temperature, we're going to shift away. If I decrease temperature, we're shifting towards. K increases. And for this one, K decreases. Okay, catalysts. There are catalysts. I talked about catalysts when I was telling you about my research, and catalysts do not affect the position of equilibrium. Remember, catalysts only change our activation energy. So yes, it makes it happen faster, but equilibrium is not about how fast it happens. That's what kinetics is. Okay, so the reaction still happens. It just happens at a different speed, but our equilibrium is not affected by those catalysts. And that's it for chapter 15. I will see you all next time. Have a good day.